Hello everyone, I'm Hongxin from National Taiwan University. Today I'll present our paper, hKVS, a framework for designing a high-throughput heterogeneous key-value store with SmartNIC and RDMA. I'll start with the overview and the background of this research. In-memory key-value store is a simple form of database which stores data in key-value pairs. Because it stores data in memory, it can provide high throughput and low latency. Some popular examples in the industry include Memcached and Redis. Prior studies by Facebook and Twitter have shown that the size of key-value pairs stored in these databases are small. Most of them are less than 1 kilobyte. Moreover, most of the key-value store workloads are read-heavy, and their access patterns are also highly skewed, where most data access correspond to a small number of public keys. Many research work have used RDMA to reduce the network overhead and improve the throughput of hKVS. Based on the involvement of server-side CPUs, these RDMA KVS can be roughly divided into server-driven and client-driven KVS. Server-driven KVS is similar to an RPC server, where a server-side CPU actively polls for incoming requests, so it has similar read and write performance, as their request handling procedures are similar. In fact, prior research showed that they deliver higher throughput in server with powerful CPUs. A well-known example is HERT. On the other hand, client-driven KVS can be treated as a remote memory, where clients use RDMA verbs to directly read or write the key-value pairs on the server memory. Writes are usually slower than reads, since they must deal with concurrent writes. Examples include Clover, Nancy, and Race. The goal of this work is to improve the throughput of KVS running on hosts with RDMA and SmartNIC. Note that in this context, we measure the throughput with RPS instead of network bandwidth, as it is quite easy to saturate the network bandwidth when the size of key-value pairs are large enough, say 1 kilobyte. As discussed earlier, RDMA have been widely used to improve the throughput of KVS because of its high message rate and low latency. On the other hand, SmartNIC is a SoC containing CPU, memory, and high-performance NIC. They are often used to overload tasks from hosts. hKVS combines the host and SmartNIC to build a heterogeneous KVS, and uses RDMA to achieve high throughput on the host and the SmartNIC. hKVS runs one KVS service on each of the host and the SmartNIC, and offloads some requests to the KVS service on the SmartNIC. The design space of hKVS has several dimensions. How to design the RDMA KVS service on the host and SmartNIC. How to determine the request to be offloaded. And finally, how to maintain the data coherence between two KVS services. In this paper, we'll focus on designing hKVS for workloads that are read-heavy and skewed access. In this section, I will show the throughput of different KVS on the NVIDIA BlueField 2 GPU. We hope to answer the question of how to design the KVS service on the SmartNIC by comparing the throughput of server-driven and client-driven RDMA KVS on the BlueField 2. We use HERT and Clover as the representatives for them. The setup consists of a client node with a 60-core CPU and a BlueField 2 SmartNIC equipped on another node. Both of them have a 100 gigabits per second RDMA NIC. The size of each key is 8 bytes, and we use two different value sizes to observe the performance difference in different scenarios. Besides, the access pattern follows Zipf distribution with parameter 0.99, and we test with three different read-write ratios. Experiment results show that Clover performs better than HERT in read-intensive workloads, but HERT significantly outperforms Clover in write-intensive workloads. As shown in the top right figure, Clover can achieve 31.6 million RPS in read-only workloads with 32-byte values, where the performance is bounded by the message rate of RNIC. On the other hand, the performance of HERT is bounded by the ARM CPU on SmartNIC, so it can only reach 15.5 million RPS at most. However, with 1 kilobyte values, Clover and HERT deliver similar performance, as the throughput is bounded by the network bandwidth. The results show that running client-driven KVS on SmartNIC delivers the highest throughput. Therefore, we designed the KVS service on SmartNIC based on Clover and offload requests to that KVS service. Next, I'll introduce the design of hKVS. The KVS server of hKVS consists of two KVS servers: the primary KVS service on the host and the secondary KVS service on the SmartNIC. Primary KVS service, or PKVS for short, is a server-driven KVS which can serve all read and write requests. In addition, it also identifies the popular keys and replicate or synchronize them to the secondary KVS service. Secondary KVS service, or SKVS for short, is a client-driven KVS which only serves read requests for the popular keys. Since we target read-intensive workloads and skewed access patterns, serving only read requests for popular keys can cover a significant portion of all requests. The client interacts with the KVS server as follows. Initially, the client sends its request to the PKVS. PKVS then updates the access counter to find the popular keys and perhaps replicate or synchronize the data on SKVS. When responding to a request, PKVS sends a replicate flag in response for clients to update its lookup table. For a future request, a client can tell if the key is available in SKVS by checking the lookup table, and it can offload the request to SKVS if PKVS is busy. PKVS consists of service thread and sync threads. Service threads are responsible for handling the incoming request and identifying the popular keys. To replicate or synchronize the popular keys to SKVS, service thread includes sync requests to the synchronization queue. Sync threads then process the sync request in background and notify the service thread when they complete. Service threads are based on the worker thread in herd. Clients use RDMA write to send request payload to the buffer in target service thread. Service thread then pull the buffer and reply with RDMA send. Each service thread holds a partition of the key space and stores those key value pairs in a local KVS. Besides, they determine the popular keys with moving window access counter, which will be covered later. We co-locate the metadata server and the data storage of Clover on a SmartNIC to form the SKVS. It only serves the read request of popular keys, as the memory on SKVS is small. Note that PKVS is the only writer in this scenario, which avoids conflicts caused by concurrent writes on a specific key, since the ordering can be serialized by the service thread in PKVS. As mentioned in the introduction, a coherence mechanism is required to synchronize the data on a PKVS and SKVS. Ideally, we would like to employ a strong consistency model. However, since the write performance on PKVS is much higher than SKVS, strong consistency will incur high overhead as the PKVS cannot reply until the write on the SKVS completes. Therefore, we adopt the eventual consistency model, which ensures that PKVS and SKVS will have same data after a certain period. Such consistency model enables a synchronous update, which can reduce the latency and increase the throughput of PKVS, despite that SKVS might return slightly older data. We restrict the size of its synchronization queue to mitigate the inconsistency problem. The last question to answer is deciding the request to offload. We aim to maximize the fraction of offloadable requests given the small memory on SmartNICs. We adopt common techniques used in cache design to determine the popular keys and copy the values of those keys to SKVS. First, we use the moving window access counter to ensure the offload keys have been accessed multiple times recently. In our evaluation, we configure this admission policy to require that popular keys must appear at least 4 times in last 800,000 requests. In addition, we remove the least recently used keys when reaching the size limit. Once evicted, the key will be invalidated in the SKVS, as it won't receive future update. We then conduct several experiments to evaluate the performance of hKVS and compare the results to their theoretical bounds. The setup consists of a host equipped with a 60-core AMD CPU and a Bluefield 2 DPU. We use 3 client nodes, each runs up to 24 threads, that is, 72 threads in total. The PKVS running on the host uses 32 service threads and 24 sync threads, which is shown to deliver the best performance. Finally, the access pattern of the workloads follows the Z-film distribution with parameter 0.99. First, we measure the throughput and latency of read requests in pKVS to observe the impact of public key selection. We adjust the load by changing the number of client threads to produce different data points in the figure. Results show the public key selection with access counter adds around 1 microsecond to the request latency, and there is a 10 million RPS drop in maximum throughput. Next, we observe the synchronization overhead by measuring the performance of write requests with similar approaches. Thanks to a synchronous update, enqueuing sync request only adds 0.2 to 0.3 microseconds to the latency under light load. Although the maximum throughput has a huge drop due to the slow write in hKVS, many production workloads are read heavy, so the impact is not that severe for those workloads. Finally, we compare the throughput of pKVS and hKVS to their ideal value. Here, we use the throughput of herd and cover as their ideal KVS, where no synchronization and public key selection occurs. With 32-byte values, the throughput is bounded by the CPU and the message rate of RDMA NIC. In read-only workload, hKVS can achieve up to 91.5 million RPS. With 95% read workload, the total throughput drops to 45.2 million RPS, which is bounded by the write throughput of hKVS, and pKVS is also bounded by the slow write of hKVS. With 1 kilobyte values, the throughput is bounded by network bandwidth, and hKVS is able to deliver close to ideal performance. With 95% read, the difference between ideal and actual throughput is 11% only, and the actual throughput matches the ideal throughput in read-only workloads. Comparing to a standalone host server, which is the state-of-the-art RDMA KVS implementation, hKVS can achieve up to 1.26 times higher throughput with 32-byte values, and up to 1.86 times higher throughput with 1 kilobyte values in read-only workloads. In 95% read workloads, hKVS also achieves up to 1.48 times higher throughput. Finally, I'll wrap up this paper and discuss possible future works. hKVS is a cost-efficient approach to improve the throughput of RDMA KVS. We can easily and efficiently scale the throughput of RDMA KVS running on a host with one or a few SmartNIC, which costs around $2,000 only. As long as the synchronization overhead is low, this hybrid architecture can deliver high throughput. Future research may further explore the design space to adapt hKVS to more types of workload by making different choices in those dimensions. For example, we could build a SKVS with high write throughput KVS to make hKVS perform better in write-heavy workloads. Future work can then leverage the evaluation approach presented in this paper to quantify the gap between ideal KVS and actual performance. Thank you for listening, and I hope you enjoyed the presentation.